Good morning. All right, so I'm going to be talking about video game stuff today. So as was already announced, I am Ron Bose. I'll have my contact information on the last slide if anybody wants to find me later. I'm originally from Winnipeg. I'm Canadian. I live in Seattle, and I come to Montreal for vacation. I come here to practice my French, which it turns out is really bad, but I try. I don't really try. But I took 10 years of French in school. You would think I'd be good at it by now, but nope. So I spend my days working for CounterHack. We make a bunch of different hacking games. NetWars is one of them, Cyber City and all that stuff. It's all different SANS products. Outside of work, I do DNS Cat 2, which is a DNS tunnel, and kind of how I got introduced to Montreal hacker scene to begin with. And I love reverse engineering, taking apart tools. I just did some firmware reverse engineering for work a couple months ago, and fuzzing firmware and finding vulns and stuff. It's pretty cool. But I originally got into information security via game hacking back in the early 2000s, which is where this talk is going to sort of focus. So I'll be talking about video games and what we can learn from them. Some hacks, cheats, whatever. As I said, I did video game hacking before I did real security, and I think that gives me some kind of unique insight and some interesting things to talk about. And you know, as a kid, my dad always told me, "You're wasting your time with these stupid games." But here I am, so take that. So there's not going to be a whole lot of new and unique research. There's going to be a lot of history, things that were never documented. I try to find a lot of information about some of the balance hacking and stuff like that from then, and there's nothing online anymore. It's all lost to history. So I'll be talking about some of those things that nobody probably knows about anymore. Give you guys some knowledge, some new things to think about. Hopefully I do that. But in reality, I just wanted to watch YouTube all day and then call it research. So let's talk about the motivation of game hacking. So fun and education, and that's kind of why I got into it. I was in high school, I was bored, I wanted to do better at video games, so I learned how to write cheats. I'm sure anyone who's played Mario World as a kid has probably gotten stuck in a wall at some point or whatever. And some people take that and figure out how they can use it to either beat levels faster or get code execution or something. It's also a great place to learn hacking skills sort of safely. If you're trying to learn hacking by hacking websites or whatever, you're obviously going to get in trouble, or your school sites is even worse. But video game stuff, as long as it's on your own machine, it's pretty safe. No one's going to get mad at you for it. So it's a good place to learn a little bit of reverse engineering and how do you edit your save file to give yourself more lives, or how do you whatever. And there's also speedrunning, which is a huge thing. I have a little video here that's probably not going to work because I put my phone in airplane mode and I was tethered to it, but it doesn't matter. I could do a whole talk on speedrunning, and I was actually planning on doing a lot more about speedrunning, but it turns out that standing here and talking about video game speedrunning in slides is really boring, so I decided not to do that. But a lot of the glitches I will talk about are ways to beat games faster, and I'll have a bunch of links throughout to different things that I think are worth looking at. This one, for example, a Mario 64 speedrun. Speedrunners often almost exclusively use built-in features. So they look for things that are in the game. And the example I have here, which might work on my other tab, is in Mario 64, when you jump, you gain speed, but they don't want you to go too fast. So they subtract speed from you. They subtract velocity from your speed. But if you jump backwards, they still subtract velocity, and therefore you can go infinitely fast backwards. And let me just see if this actually loads in the other tab. Yeah, I don't know how far it'll play, but I only want the first 30 seconds anyway. This looks okay on the projectors, right? I can, yeah. So you'll see him going to an edge and jumping backwards. And by doing that, they gain infinite speed and can jump through walls. So it's kind of like misusing a feature of the game. So, presenting again. I've also got a Breath of the Wild, I'm going to turn off airplane mode just because hopefully it doesn't interfere too much. So, yeah, Breath of the Wild, just this week somebody discovered a glitch where, I don't know if you guys have played this new Zelda game, but if you freeze something with a stasis gun and whack it a bunch and jump on it, you can go flying around the world. And people found new and interesting ways to do that. And that link there, I'll give you my slides afterwards, but that link there is a really cool demonstration of that. Another big thing about game hacking is interoperability. which is writing clients that weren't intended to be written. So I cut my teeth, as I said, on Battle.net hacking, StarCraft, Warcraft 2, Diablo 1, Diablo 2 a little bit. The really old Battle.net stuff used to have a huge community of players, tens, thousands, millions of players, and the games all have pre-game chat rooms where you could find people, meet people, stuff like that. But there was very limited operations in the sense of banning users, muting users, all the new stuff you get with Slack and even IRC and stuff. But the problem is the person who got the ability to moderate channels was the first person there. So if you disconnect and close the game, somebody else takes over your channel and bans everybody, and that's not great. So people wrote bots. Initially, these bots use a chat gateway where you telnet to useast.battle.net on port 6112, and you type a keystroke, you can say, I forget, Control-D or something, and then you can chat with people just like normal, just plain text chat. The problem is that this very quickly became a source of spam. People would write spam bots that would log into this protocol and just make noise and stuff. So Blizzard, to fix the spam problem, just prevented these guys from doing anything. Now suddenly, everyone who wrote these bots that would moderate channels and stuff couldn't use it anymore for those purposes. So instead, people started writing bots that would emulate the game clients. So we would reverse engineer the StarCraft game and say, how does a login work? It connects to the server, it gets updates, it verifies your CD key, it hashes your password with SHA-1-ish. Not quite SHA-1. It's SHA-1 with a bug, I guess, is how it works. And that was fun to reverse engineer. But there's a whole bunch of stuff. And then as the spam bots took over, Blizzard would add new things. For example, when you were logging into the game, it would take a screenshot, hash the screenshot, and send it, which prevents you from using a bot unless you just take a screenshot yourself, which everyone just did. So there's a whole bunch of really cool stuff like that. And on the topic of Battle.net, that's talking about pirate clients a little bit, and that was a big deal, and I'll talk a little bit more about that later. But there's also pirate servers. So when Warcraft 3 came out, there was a big beta where everyone wanted to be part of the Warcraft 3 beta, but they only picked like X thousand users or whatever, and they gave them beta access to the real Warcraft 3 servers. The problem was everyone wanted to play, so people were setting up their own servers with their own worlds or their own matchmaking services and stuff. BNetD, I think, was one, and there's lots of others. But basically, Blizzard wanted to prevent people from using it, so they added an encryption thing, which I'll talk about shortly. Of course, they made a mistake in the encryption thing, and that made it possible to still do it. So I think that's the next thing I talk about, actually. One funny little note, Battle.net back in those days, you would log in, you would send it like, hey, I want to connect, and they would send you back a chunk of code to run and say, run this code to verify your version. This is not a signed connection, it's not encrypted. It's just plain text code on the network sent to you. This is 2001 security. And then the last motivation is profit. World of Warcraft farming, when it came out, writing bots that would go collect gold and then sell gold could literally lead to actual money. There's also pirating games. I'm going to talk a little bit about bypassing CD key checks and stuff a little bit later. And this is where it gets into legal gray, well, not really gray territory, black territory. But pirating games was a big thing, still probably is a big thing. And then speedrunning, I talked about already. People who are really, really good at speedrunning can make a lot of money. There's Twitch sponsorships, there's all these things. But there are two very famous speedrunners, Billy Mitchell and Todd Rogers, who just this year had like 30-year-old records revoked for cheating. And it was very obvious to everyone in the community that they had cheated for these records. But the official, like, one was in Guinness, one had a documentary made about him, the King of Kong, about these very well-known cheaters. And they finally were actually revoked, had the records revoked and stuff this year. So the two links at the bottom, if you watch them later, are really, really interesting, kind of 10, 15-minute backstories on how they cheated. One used like fake arcade cabinets. One just said he got a low record and no one verified it. It's the Dragster speed record. It's very famous if you look it up. Yeah. Anyway, let's talk about bugs. So I just started with something really simple. If anybody here has played the Deus Ex games, a big part of the games is the fact that you can take multiple paths to everything you do. One path is to take your guns out blazing and shoot everything and break in, blow up doors and all that. The other one is to look for people who leave notes all over the place with passwords on them. And this is very much like real security. This text is really small, but it says, okay, I'm ready at my end. If you can't get it, if there's any errors in the console, log in using CLOD04SF, blah, 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 blah. This is in a game. It lets you log into the system. In real life, the exact same thing happens. People leave their passwords every which place. So I thought that was just a really nice, simple little intro to this. The first thing we talk about in a more detailed way is bad crypto. So this famous XACD, we need millions of dollars of hardware to crack this password or a $5 wrench. So we're going to talk about Battle.net again because that's what I like talking about. So it turns out cryptography, as I'm sure you guys know, is really, really, really hard to get right. I wrote a whole talk about it and gave it a ShmooCon in 2013, 5 years ago, which is a little bit scary. But crypto is used all over the place in browsers and applications, in games. It's used for protocol protection, password hashing, to verify clients aren't hacked or aren't modded or whatever. It's used to verify servers aren't sending you evil code. It's used for a million things. The example I'm going to start with plays off the Warcraft 3 pirate servers I was talking about a minute ago. So as I said, when Blizzard released Warcraft 3, it came with a very exclusive beta that wasn't available to most of the players. Naturally, people wanted to make their pirate servers, so they did. However, Blizzard really wanted to prevent this from happening, so they added in security checks. So I used to have like 5 slides about this with all the math, but it's really boring. When the user connects to a server, the server encrypts its IP address and sends it to the client. The client decrypts the IP address and verifies it. That's how it verifies it's connecting to the real server, because nobody else has the encryption key to encrypt their IP address. The first mistake, encryption is not integrity. If they want to use encryption for integrity, they need to sign it with an HMAC or something similar. But if they had an HMAC, they wouldn't need the encryption in the first place, because all they want is integrity. There's no secret about the IP address. So why they use encryption rather than signing? It's a mystery. The second mistake is when they validated the IP address, they would take the IP address, which is 4 bytes. This predates IPv6. Everything predates IPv6. But they would take the 4 bytes, they would pad it with 1,020 bytes. They would encrypt it, send it to the client. The client would decrypt it and verify the first 4 bytes are the IP address, and then stop. That means that an attacker could generate a valid encrypted block in less than 2 to 32 tries, or 2 to 31 tries on average. So they made a classic RSA mistake, which is they did not verify the padding. So here's my implementation of it, which I wrote in Java op, a Battle.net operations bot. The source code is at the bottom there. But the way I implemented it was I took the length of the result, and I filled the rest with the proper padding, B, 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 and then I verified it. The problem, I was writing this talk and saying, okay, Blizzard screwed it up. Here's their stupid thing. I did it right. Here's my thing. But as I'm writing these slides, I look and go, this has a bug in it too. Because if you look at byte correct result equals new byte result.length, result is attacker controlled. So I create my byte array the same size as the attacker wants me to. So I had a vulnerability in my code too. It just goes to show encryption is really hard to get right. So lessons from this section are crypto is really, really hard, and RSA is ridiculously fragile. There's very few people in the world who know RSA well enough to actually use it for proper encryption and not have vulnerabilities. I tweeted about this yesterday, thinking it's kind of funny that my code had a vulnerability in it. And my friend replied with a really great quote, which is, RSA is harder than RC4, yet everyone here hates RC4, but everyone seems to like RSA, and it's a mystery why. So yeah, the lesson here is don't use raw encryption, basically. Let's talk about encoding bugs. If anybody's ever written code that uses Unicode or UTF-8 or UTF-16 or other languages, I guess having the French language side here probably run into this more than I would. The encoding is really hard, and we're going to talk about a few issues. So, as some of you here know who know me, I always talk about DNS when I do talks because I like DNS a lot. And as I said earlier, the reason I'm here is probably because of DNS. So we're going to talk about an infinite recursion bug that's very common in DNS, and then how this sort of bug led to a remote co-execution in a really, really, really popular DNS server. So I had like 10 slides explaining DNS compression, I realized I had to compress my compression talk. So this is my one slide explaining it. Basically in DNS, I'm assuming you guys know the basics of DNS, which is that you want to know the IP address of a server, you send it the server's name, and it sends you back the IP address. The problem is when the server replies with the IP address, they reply, you say, what's the IP address of google.com? And they reply, you asked the IP address of google.com. Google.com has the following 10 IP addresses. Google.com is at X, Google.com is at Y. They say the same thing over and over and over in a packet. DNS, RFC 1035, was invented back in the 80s, and as a result, those extra 30, 40, 50, 100 bytes in a packet are a really big deal. So they added a thing called compression. If you read RFC 1035, you'll read all about this. But the essence is, when you encode a name, I'll use my own domain as an example, it takes each piece of the name, www, skullsecurity.org, it prefixes a length, and then sends that. If a length starts with 2 1 bits, which is C0 usually, but it could be C1, C2, C whatever, it's treated as a pointer. So for example, if I have hex characters 3, www, then C00C, that tells the parser, look at offset 0C for the rest of this message, or the rest of this name rather. But what if we put C00C at 0C? It's going to jump to 0C and say, oh, I got to jump to 0C. Oh, I'm going to jump to 0C, and so on. And it'll infinitely recurse. There were, especially in the older days, there were a lot of parsers vulnerable to this. The Nmap DNS library was vulnerable to this originally, and lots of others were, I'm sure. But what's interesting is, I was reviewing DNSMask at a previous job, and DNSMask is used by about 1 billion different devices. Most routers, most servers, most everything, Ubuntu, Debian, all come with DNSMask pre-installed and running. I was looking for vulnerabilities in this with a fuzzer for a project at work, and I found I was able to crash it with using weird pointers. When I actually investigated this vulnerability, I discovered that there was a limit, 1024 jumps. So if you have a 0C, C00C at offset 0C, it would jump 1024 times. You would get ... Then it would stop and say, this is an invalid name, go away. The problem is, if you look at this code here, the very first line is, sorry if it's too small, but the very first line is name length plus equals length. So it keeps track of how long the name is. It's doing that to make sure we don't overflow a buffer. The buffer is 1200 bytes long, something like that. And name length plus equals L is checked against max dname, which is 1200, to make sure we aren't overflowing the heap buffer. The problem is lower on, we see that this for loop at the bottom, loops L times, which is the length of this name segment. So www, it would loop 3 times, and add each one to the answer. Then at the bottom of the loop, it adds a period. That period is not tracked anywhere, which means if you have www.google.com, it thinks there's 3 plus 6 plus 3, which is 12 bytes. But because there's 2 period, it's actually 14 bytes. Because the buffer is longer than the DNS packet, this is not exploitable directly because you can't. But with the recursion, you could set up a very specific recursion such that it adds 100 bytes, then loops 1024 times, and therefore it adds 1 million bytes to the packet, and therefore you can overfill a heap. So very indirectly, this encoding bug and this length bug, whatever you want to call it, led to a stack overflow. So that's kind of a really neat vulnerability with encoding in the real world. Then let's look at one in games. So in a very, very similar bug, the original StarCraft, I hadn't actually intended this talk to be all about StarCraft, but it turns out that's what I hacked when I was a kid, so that's what we get. So StarCraft has low ASCII characters available, where you can send color codes, you can send alignment, you can send line feeds, all this stuff. You could do this in messages and names. We'll get to more of that later when we talk about other things. But there was one low ASCII character, 0C, coincidentally, which when the client rendered it, it would, because it was never used for anything, no one ever tested this, and it would parse a character, but it wouldn't increment the pointer. So it would parse a character over and over again and lock up any game client that saw it. So if you were to send people a message saying, hey, my name is 0C, it would infinitely loop it, and the person would basically have to kill their game, control, delete, and kill the game client. So of course, as a young hacker, we used these things to make people leave games when we were sick of them. A funny side note on this is, if you send a message to somebody else, you crash yourself too because you see your own messages. So you have to have a little filter string, which is at the bottom here, to filter out any character. And we'll talk about how colors and line feeds can do fun stuff when we talk about client-side security. Hey, client-side security. So I was sitting yesterday morning in Starbucks trying to put funny pictures in my slides. And I'm thinking, how do I explain client-side trust in the picture? Then I looked at my cup at Starbucks and it had the wrong name on it. My name is Ron, not Rob. I'm like, hey, client-side trust. They just trust my name. So I thought that was kind of a funny way of introducing this. So back to StarCraft. StarCraft has two modes. When you log into Battle.net, I talked about this already, you send your CD key, you send your password, you send all this stuff and all whatever. That stuff you log into with a chat server and it's a matchmaking server, nothing else. When you're actually playing a game, Battle.net only knows that you entered the game. At some point in the future, you left the game. But in between, it doesn't know what's going on. So I found this little diagram of a peer-to-peer network. Basically, I love most modern games are the left side here. There's a server which all the clients send stuff to, and the server multicasts and holds the game state and everything. But in StarCraft, there's no server in the middle. It's entirely peer-to-peer multicast style. So when you join a game, here's just one of many, many, many examples of what you can do. When you join a game of StarCraft, you send to everybody, hey, my username is Ron, or I used Yago back then and stuff. It's like, hey, my username is Yago. That username is registered with Battle.net. It's got a password. It's got all this stuff. But when you actually enter a game, nothing verifies that. There's nothing stopping me from saying to everybody, like, hey, my name is my friend's IDA. My name is Blizzard staff. My name is computer. And you'll join the game, and everyone will say, hey, computer just joined the game. Or, hey, Blizzard staff just joined the game. Imagine being like a 17-year-old gamer able to join games as Blizzard staff. Just think of all the havoc you can cause. And we kind of did. This was literally my first introduction to any sort of hacking whatsoever, was the SCBS NIC spoofer. Basically, it was a VB6 app. There's a link to it at the bottom there. I'm so happy at this point I kept all my code from 20 years ago. But this is literally, my friend wrote this tool which would log in, which would read StarCraft's memory, find your username, and replace it with anything you wanted. It was a super simple app, but I was like mesmerized, like, how do you do this kind of thing? And he actually sent me the code for it, and I got to learn how like the Windows read process memory and write process memory works. And this was like literally my first introduction to any kind of hacking. And I went with that. So as I mentioned, low ASCII characters are color codes. You could set your username to OC, so when you join a game, everyone's clients crash. And that's hilarious, but it doesn't really do much fun. What's more interesting is to make your name, for example, blue, Blizzard staff, or yellow, computer, and suddenly you're doing really weird things that nobody would ever expect. And you can really mess with people. For example, if you send 10 line feeds, it hides your name, and then center, and then white, and then nuclear launch detected, everyone in the game would think a nuclear launch was detected. You can send uploading virus. You can send computer has entered the game or left the game. You can send Ron has left the game and then stay in the game. You can do all kinds of really neat things. As far as I know, I was the first person to do this on Battle.net. I used the exact same thing that Yoshi's NIC spoofer did from the previous slide. I would read memory. I would look for a key character. I would type ABCD or something. When the program read the memory, it would replace that with whatever I wanted. Really small text here, but /nuke would send nuclear launch detected. /cheat would send cheat enabled. /leave would say your name has left the game, and so on and so on and so on. It was really, really, really entertaining back then. Another thing about this, because there's no authoritative server, every single game client in StarCraft is this little mini authority. It knows the game state of itself and of everyone else. That means map hacking. I don't mention it in the slides, but being able to see the entire map, it has to be possible because there's nothing, every client has to know every other client's doing, so there's no secrecy if you have the right tools. But what this also means, because every single person has state, if one person has the wrong state, they desynchronize and they get kicked out of the game. You can make sure people have the wrong state by just saying them the wrong message. So the easiest way to do this, the protocol for games, I don't get into that at all in this, but it's just you broadcast messages on UDP, and there's a little checksum, and then data, and a bunch of other. They basically influence TCP over UDP for some reason. But all you have to do is just remove the data and update the checksum, and suddenly you start telling one player you're doing nothing, and everyone else thinks you're doing everything. Before you know it, they have a different game state, and they get kicked out of the game. And then, if they're beating you, now they're not. Then, finally, for this little section, post-game shenanigans. So the matchmaking service of Battle.net puts you together into a game. You play the game. You can do anything you want because it's all synchronized. And by the way, that synchronization means you can't you can't spot units. You can't update your resources and stuff like that, because then you're already synced. You get kicked out. As soon as you spend money you don't have, you get kicked out. So you can't do a lot of things like that. But you can do a lot of other stuff. But after the game, every client exits the game and then says to the Battle.net matchmaking service, hey, I won, and this person lost. There's nothing stopping you from saying, hey, I always win, this person always loses. So when you leave a game, and if we did this, we would make sure that everybody said, I always say that I won. If I say I won and everyone else says I lost, I get a disconnect, which is just, it's not a win, but it's not a loss. So you could very easily have a record of like 10,000 wins, 0 losses, and a lot of disconnects too. So it's kind of cool that they just trust the client is valid, and there's nothing making sure you're valid. As a little bonus at the bottom here, if you do set your name to like Computer in yellow or Blizzard in blue or whatever, when the other players send back the results, Blizzard goes, that's an illegal name after the game, and then kicks them off Battle.net for an hour. So it's a little bit rude to do that, but it was kind of funny too. So I mentioned emulation bots earlier. When you emulate the game client, you can do things like, I'm going to log in with my account 8 times, and then I'm going to join a game, an 8-player game with myself 8 times. I'm going to play the game for the minimum time, which is 2 minutes. Then I'm going to leave the game and say, hey, everybody won. And then you have 8 wins added to your record. A friend of mine, Skywing, he works at Microsoft now, he made an account called WinBot, which literally went online, played against itself, restarted over and over again, until he had a record of 1 million wins and 0 losses. And then one day we woke up and he had 1 million losses, 0 wins. I guess somebody at Blizzard caught on and thought they'd be funny. I really, really wish I found a screenshot of this. I emailed him. No one has any screenshots left. I found people talking about this online, but I couldn't find anybody with a screenshot, which is really unfortunate. So that's the game side of client-side trust. Let's talk about a couple of real-world client-side trust issues. I'm going to talk about 2 projects I worked on at a job from a million years ago. My second InfoSec job. So these screenshots are from a presentation I gave like in 2005. So there's going to be really bad quality screenshots. But anyway, I don't really have an introduction slide to this. But basically, we had a security camera that was monitoring a location. And we wanted to make sure that the web interface for the security camera was secure. Application security is our jobs. So keep in mind when I'm explaining this is 2004 or 5, in there somewhere. No, or maybe 2007. In any case, I get to a login form. I type admin because that works 90% of the time. And I get login failed. Too bad. What I noticed immediately was that the login failed dialog had absolutely no lag, which told me that the authentication is happening on the client side, not the server. So what do? Let's look at how this works. I'm sure most of you are thinking JavaScript issues, but this was before JavaScript existed. Well, that's not true. This was before JavaScript was popular. So I dig down, and it's an ActiveX applet. Some of you are probably too young to remember ActiveX, but here's how it worked in essence. The website would give you a DLL file that you would load into the process memory of Internet Explorer. It would run machine code in your browser and then do stuff. That's what security was like 10 years ago. Literally code running in your browser. How was everybody not hacked back then? Anyway, so I opened a DLL file in IDA. This isn't the real software anymore. I made my own like imitation of it to make sure I didn't reveal anything that I shouldn't have. But in essence, I would look at the strings window. I would see login failed. Please enter a different username and password. The first thing you always do is search for error messages or search for log messages or search for whatever. So you jump to that. You find a security check. It does a comparison, it does a jump, blah, blah, blah. I don't want to go too much into assembly code right now. You replace the jump, which is 75 OE in memory. We'll talk about machine code later. With 9090, which is nop nop. Basically, remove the security check, and then log with the min, login successful, and yay, there's your camera. This literally worked. We were actually able to log into a security camera like this, and see all the cameras, control them, move them, laugh at people walking around, all that kind of stuff. So we reported this to the vendor, and the vendor said, that's way too advanced, nobody's actually going to do this, so they didn't fix it. Yeah. Speaking of bad vendors, this is another project from the same company I worked at, and this has been like a nemesis of mine, because I went back and forth with the company so much, because it was a sensitive application that had SQL injection all over, and it was just awful, awful. This was another one where it was running server-side binaries with Stack Overflows. It's like literally Stack Overflows in a web app. Like, security in these days was hilarious. So last week I went to the site again to see if it still exists. And it does exist. And when I looked at the disclaimer, it said, I just had to put this in because it's funny, they had a thing called computer viruses in the ULA or whatever. Every reasonable effort has been made to ensure that the information provided on website does not contain viruses. However, secure yourself. Basically, it's saying, we're not going to give you a virus, we promise. Like, that was kind of funny. Anyway, so this is the real login form now. It was a lot different back then. But I don't have permission to test this anymore, so obviously I didn't do anything with it. But basically, back in those days, I would put quotation mark test, the username or in the password field, and you would get a SQL error. And you could do SQL injection to the username or the password field. So I reported this to the vendor who made this application, and they said, this is not exploitable because you limit the username and password fields to 8 characters. First of all, I don't even know where to start. So I looked at this last week, and that was 15 characters, so it's 87.5% more vulnerable by my math. So yeah, where do you begin? You begin by changing the max length field in the HTML to 100. And even if it's a server-side check, you can still do, shutdown is only 8 characters, so you can still do things like that. So there's like a million examples of client-side security issues. These are just a couple I thought were kind of funny from a long time ago. I've very barely talked about these in the past 15 years of doing talks, so I thought I'd kind of bring them up and talk about that. Let's talk about some injection attacks. So I was looking for a picture for this slide. I spent yesterday putting pictures on slides, and then a coworker was laughing. In this picture at the bottom, the middle guy is the governor of Delaware, which is a state, I'm told. And my coworker, Tom Hessman, happened to have his name on a chalkboard behind him, so he injected his own name into the governor's picture. Tom Hessman photobomb. So we talked about injection a little bit already. Injection is basically, well, we'll get to injection is after, but being able to enter colors in your name is injection vulnerability. You're putting formatting characters in a place where none are expected. The message spoofing is an injection vulnerability. You're putting format things where they shouldn't be, stuff like that. So just a few examples of injection, then I'll get to some hard examples. I said message spoofing, SQL injection we talked about, that's a form of injection, cross-site scripting, Stack Overflows, and so on and so on and so on. So the example I'm going to give next is not really injection, but I wanted to talk about first how code and data, as far as machines are concerned, are the same thing. I showed you how you knock out the jump in the earlier slide. Let's look at more details on how that works. So there's this game I played when I was a kid, and I've since bought it, so don't worry, this is, well, whatever. But I won't name it because I'm on camera, but basically there's an old shareware game where it would pop up a box saying, register this copy. So you download the game, or you get on floppy disks. Floppy disks for the kids in the audience are these devices you buy at stores. So you would get this game, you would install it, and it would say, you can play the first 3 levels, and the next 10 levels are not available because you haven't paid for the game yet. When you pay for the game, you fill a form, and you mail it in an envelope to this company, and they mail you back the code to use. So when you click on please register, it says, here's your code, 18153 is the one I got when I made this last week. So it will give you a code, and you have to enter your key, which is another 5-digit number. So what do you want to do? We're going to talk about how you would bypass this check, obviously. So you go to source code, you search for the word registration, or sorry, the disassembled code, the assembly code, and I don't want to talk too much detail on how you do all this stuff. This is a whole talk on its own. But essentially, you go into the assembly code, you search for strings like your registration code, and you find it. So I see your registration code is %D. That's a C string formatting character. Then you figure out where that's used, and what you see is I named things on this just to make it more obvious, but you see a little function. This is assembly code. Doesn't matter how it works. Basically, it takes the generated code, it passes it to a function, then it compares it to what you typed in. So if your reg code is 1, 2, 3, 4, 5, it takes that, it passes it to a function. The function return value is, say, 5, 4, 3, 2, 1. Then it compares that to the thing you typed in. And if they're the same, yay, you can play all the whole game. The easy way to bypass this, obviously, is to change the jump to say, no matter what I enter, just play the game. But that's not that interesting. I want to talk about how this code works. So what we do is we go into the function that generates the code. It takes in the code they give you and pops out the code that you need. So you open up the function, and on the left here, you see machine code bytes. These bytes are no different from data bytes. When you run the executable, it loads in the memory, it takes these bytes, it runs them, it gives you the output. So what we can do is copy and paste these bytes into our own program, which is what I did right here. So I just made a character string. I just literally took the assembly code from them, copied it, pasted it, and made it a function pointer. I ran it, it gave me a code, the code worked. The reason I talk about this is to show you how like the code you see here, which tells the CPU to do stuff, is the same code you see in a string. So when you do a Stack Overflow, you're just saying a bunch of bytes and tricking the machine into running them. Data and code are the same thing. That's sort of the lesson with that. Yeah, that's what the slide says. If you're interested in learning Stack Overflows or memory access bugs or anything like that, this is the first thing to know, is how code and data are interchangeable. So we'll see if this video works, but this is essentially what happens with some of the Super Mario World glitches. And this is kind of a really cool one. I think I have it open in another tab. So basically, this is a world record attempt at Super Mario World, which is the Super NES game from way back when. And this particular attack was done many, many times using a computer, using a tool-assisted speedrun, a TAS or whatever. This is the first time a human ever did it. I'll explain how this works afterwards. But he creates a game, timer starts, he goes through dialogue, blah, 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 blah. There we go. So he starts the first level, and you can see he does a bunch of really weird things, and we'll talk about why in a minute. But essentially, he's putting all these different sprites at the right offsets. The X value, the left-right value of each sprite, is interpreted as code later. So the fact that he's eating things, blowing things up, all this stuff, what he's doing is making sure the sprites load into the right slots so that their X values are in the right order and everything. And I'll show you what that means after. And he won the game in 47 seconds. So there you go. So I think I'm getting close to the end, and I have lots of time, so I'll show you the explanation video. I think the next slide here is just, yeah. So effectively, what he's doing, and this is a bit of a different one. This is a mushroom rather than the whatever he did, but same idea. He's telling Yoshi to grab the mushroom. Then he jumps off Yoshi and gets the mushroom himself. What happens is, because there's no longer a mushroom on there, this sprite slot becomes empty and there's nothing to be eaten. So the next thing that loads, which happens to be the football guy, Chuck, he just happens to be the next thing to load, so he gets put in the same slot, and Yoshi eats a thing that's never supposed to be eaten. As a result, it calls code in memory that doesn't exist, and therefore does arbitrary weird things. This is a time of check, time of use bug, which means when Yoshi grabs the thing, it says, is Yoshi allowed to eat this? Yeah, it's a mushroom. Then when it gets replaced by the Chuck sprite, nothing ever checks if he can eat the Chuck sprite because he's already passed that check. This is a race condition, basically. So this is going to be an explanation of it. Should be open in this tab. Yeah. So what you see to the left here are the various sprites that are loaded. So right now you have 0 through 9, which have nothing loaded. Then 10, 11 are special slots. What he's doing in this is making sure that everything loads in the right order. So you'll see as he plays a level, as sprites load, they load in different slots. And you'll see the X and the Y coordinates. The X coordinates are what matters more. So he's going to kill various things to make sure that they stop moving. So the X coordinates are 10, 3C, 5A, 9D, and so on and so on. He basically has 10 bytes to write code with these. So he does that by keeping track of where everything is. When you destroy a sprite, the slot state keeps the X values. So he's destroying things to make sure that they don't move, basically. Skip around a bit. So you'll see at this point of level, this is getting towards the end, the X values have all been set. A9, 1C, 92, 75, and so on. This is the code he needs for magic to happen. And I should mention, it's a lot more complicated than all this, but this is kind of a brief explanation of it. I have a link to the video in the slides if you want to see the whole thing. He explains it really, really well. Skip, skip, skip. Now what he's going to do here is break this block. The position of the 4 blocks that pop out are basically where in memory it gets jumped to. So he has to make sure that the blocks despawn, go off the screen at the exact right time in order for it to work. Then he does other things. Skip, skip, skip. So that block right there is, you'll notice that when he hits the block, he goes off screen. He moves the camera. As soon as he goes off screen, the 4 little block fragments despawn, and therefore their memory addresses stay the same. You'll see at the right side of the screen, it's E0 for the first block and 00 for the second, and that's where it's going to jump in memory, basically. So then he despawns the chuck by going to the left. Slow motion. Yeah, this is the same thing as slow motion. So he despawns the block fragments. It has to be E something. Okay. And I don't want to go through all this, but and this way I just ran out of buffer. But this is effectively what's happening is it's now interpreting the X coordinates as, so I should say, the block fragment is where it jumps, and the X coordinates is where it runs code. So effectively, it's mixing up code and data, which is kind of the summary here. So that link's at the bottom, and I highly recommend watching the whole thing. I learned a lot, and he explains it way better than I did. So one more injection. I added this at the last minute, obviously. eFail. It was the big PGP bug from last week, where basically it was basically cross-site scripting an email. You would send an open image, and it would interpret the rest of the email as the image and decrypt it and send it, and big deal. Anyway, that's pretty much the end. So there's a lot of things I didn't talk about. There's a lot of things in game hacking that I think are really interesting and really cool to learn. As I said at the beginning, games are a great way to learn about real-world vulnerabilities. We talked about client-side security, we talked about crypto, we talked about all these things. These are all things that apply in games, and they're all things that apply in real hacking. So I think this is a great way to learn things. And yeah, lately, speedrunning and gaming and streaming, all these things are getting really, really, really popular with Twitch, with YouTube video, whatever it's called, with all these things. It's a big deal these days, and learning how to do these things is really, there's lots of reasons to do it. So this is my contact information, my email address. Pretty much everywhere online, I'm YagoXA6. The URL here is for the talk. NorthSec Video Games is a link to the talk. So feel free to grab my slides. I'll tweet a link out later. And yeah, that's pretty much my presentation. We have time for questions.